Hey Physics 30s, it's Mr. Jukley here, going to talk to you a little bit about the photoelectric effect. That is Unit 5, Lesson 2. If you're not already there, get your workbook out and we'll jump into it. This is a pretty neat lesson, a pretty cool lesson. So, photoelectric effect in general is when we have high enough frequency EMR, and remember, we talked about last time with our photon theory, high frequency means high energy. So we have high energy photons coming in, they hit a metal surface, they can actually kick electrons out of that metal surface, and then those electrons can be used to do work and power things and stuff like that. So, photoelectric effect, in a nutshell. This was discovered by Heinrich Hertz. We've talked about Heinrich Hertz a little bit before. So Heinrich Hertz experiment was essentially he took ultraviolet light. So ultraviolet light is fairly high frequency. So high frequency. And he shone it at a charged zinc plate. That charged zinc plate was attached to an electroscope. And if you remember with electroscopes, when they are charged, the leaves stand apart. And when they are not charged, the leaves come back down together. So the leaves being these particular parts up here. So if it was charged and it was started out charged negative is what we're saying here, the leaves should stand apart like this. What Hertz saw is when he shone that UV light on the polished zinc surface, the leaves gradually came together. Now, why would the leaves come together? So if they're charged negative, they're going to be apart. If they're charged positive, they're going to be apart. The only way that the leaves of the electroscope would come together is if they're neutral. And the only way that this whole negative system could become more neutral is if electrons leave. So electrons are being kicked out. So pretty neat, Heinrich Hertz discovering that one. The photoelectric apparatus that we're going to use is sort of a simplified version. It's typically going to look something like this. So I got a vacuum tube, I got two metal plates, I got an ammeter so that I can measure current. So ammeter, remember A for ammeter, two metal plates, and then we're going to describe this having excuse me, our high frequency EMR, which right now are represented by these blue squiggles. Hitting one of the two plates, and the electrons are going to be kicked off. You might remember from Unit 4, this particular shape is going to focus them, so they move across, and they move from the cathode to the anode in this case. So overall, if electrons are leaving this side, it becomes positive, and if electrons are showing up on the other side, don't know why I'm writing electron again, it becomes negative, and then we've essentially got now like a cell where that's going to want to travel on. So electrons are going to go from the negative. They don't like being next to each other. They're going to go and they're going to refill the space back at the other side. Now, some of you might be thinking Chem 30 stuff and looking at that cathode anode. So let me clean this up a little bit here and thinking to yourself, hey, isn't that a little bit backwards, the cathode and the anode? Because all of these photoelectrons are leaving the cathode, and that's kind of the opposite of what you learned about in Chem 30, at least in terms of electrons leaving the cathode. Electrons typically go towards the cathode, right? But not inside the photoelectric device. If we're thinking about it, I'll highlight in green here, if we're thinking about just this green part right here, this part, yes, electrons are leaving, but it is becoming positive. So the electrons are going to move still from the anode, the negative side, to the cathode, the positive side. So it does actually fit with your Chem 30 stuff, just a little bit trickier to see sometimes. That being said, anode and cathode, not two terms that are going to be thrown around in Physics 30 very much, but it is good to know just in case you're confusing yourself. Cool. So this whole photoelectric effect, this is the big idea between solar cells. So solar panels, so here's some on somebody's roof, here's some on a interesting backpack. I don't know if they make these things anymore, but there's the big idea. So, excuse me, let's go through and let's try and figure this out. Let's try to explain what's going on here. So first thing I think we should talk about is, well, what would happen if we were actually dealing with classical physics? And remember, classical physics is treating light and EMR as if it was a wave. And there is, remember, evidence that EMR behaves like a wave, but is it truly a wave is the question that we're looking at here. So if an electron in the photocathode is emitted when it receives enough energy from the incident EMR, what that means for us is that, well, pretty much any type of EMR should give us photocurrent, right? Should kick out some of those electrons. Bright EMR, it should happen quicker because bright EMR in the classical theory would have a higher amplitude, it would have more energy. So it'd kick it out quickly. Whereas dim EMR would take more time, but it would still eventually kick things out, right? So that's classical, right? And then the other part with classical is, well, it should be with any type of EMR, right? Because the in classical theory, the energy comes from the amplitude. So all four of these have approximately the same amplitude as they're drawn here. So all four of those should be able to kick out electrons, right? Probably at the same rate, to be honest. Turns out this was all wrong. Every single prediction from classical physics and classical theory of EMR was wrong. So here are our real results that we've got. So in this case, we've got photocurrent, which is I, and don't confuse photocurrent with intensity, which is also I and kind of annoying, but photocurrent, which is I, and then we've got frequency, which is F. And let's check out this interesting pattern that we've got here. We've got absolutely no photocurrent to start off, and then we get to this very, very, very particular frequency, and then all of a sudden we've got steady, steady, steady photocurrent. So it's there and it's steady. Any ideas what a controlled variable for this experiment would be? So manipulated, we're changing the frequency, and we're trying to figure out what happens to the current. So current is our responding variable, frequency is our manipulated variable. The intensity or brightness is going to be our controlled variable. So assuming that it's at the same brightness, doesn't matter what frequency we are at, the same brightness will have the exact same results. Nothing below a particular frequency, and then the exact same thing above that frequency. So frequency too low, nothing happens no matter how bright the EMR is. At the threshold frequency, and that's a new term for us, threshold frequency, that's our minimum frequency to have photocurrent, and that's a definition that you definitely 100% need to know. At our threshold frequency, instantly we have photocurrent. Absolutely instantly have photocurrent. And then anything above that, as long as it's at the same intensity, we have a constant photocurrent for every single frequency above that threshold frequency. I just want to go back for a quick second here. Go back to this one. So threshold frequency is talking about minimum frequency, also called F naught. So the minimum frequency in order to give us photocurrent. Cool. How would that relate to wavelength? So minimum frequency, or what about the wavelength? And you can think to yourself, C is equal to F times wavelength. So that's just our universal wave equation. What's the relationship between frequency and wavelength? Well, it's an inverse relationship. So minimum frequency corresponds to maximum wavelength. Minimum frequency, I'm even going to write that out, maximum wavelength. Cool. So just something that'll, I'm sure, will pop up soon enough. Already kind of talked about that one. The second result that we actually saw is assuming we are above that threshold frequency, so the frequency is greater than our minimum frequency. When we have intensity versus photocurrent, it forms a direct relationship. So direct relationship means I double the intensity, I double the photocurrent. I triple the intensity, I triple the photocurrent. So direct relationship. Cool. So bright means high photocurrent, dim means low photocurrent. Nice. Kind of makes sense. All right. So I already kind of talked about that one. Something to think about here, though. So we talked about assuming that the threshold or the frequency was above the threshold frequency, we would have that direct relationship. What if the frequency of the actual EMR, so the actual EMR, was less than my threshold? Then what it would look like? If you're saying to yourself, absolutely nothing no matter how bright, you are spot on there. Absolutely nothing if it's below the threshold frequency. So a quick example here. We've got the threshold frequency for a metal corresponds to blue light. Can we describe the nature of the photocurrent if the incident light is dim violet versus bright orange. So let's go through. I'm just going to sketch those two graphs real quick. So here is current versus frequency. And we know that I'm going to use blue because it's blue. We know this graph looks like this, and F naught, or our threshold frequency, corresponds to blue light. Cool. And then the other one, okay, let's sketch this one out over here. Now I've got intensity versus photocurrent, and we know that that one is a direct relationship as long as we're above the threshold frequency. So for A, let's check out A. We have dim violet light. I think that might be purple. I hope that's purple. So violet light, I'm just going to put V. That's a higher frequency than blue light. So if it's over here, does that mean that we're going to have photocurrent? Absolutely. So violet, we have photocurrent, but it says that it's dim. So it's dim violet. That means that I'm going to have a low or a small amount of current. So I'm going to have low current, but I am going to have current. Cool. Okay, let's check out B. B was orange. Let's see if the colorblind guy can find orange on here. I think it's that. I hope it's that. If not, you'll have to pretend. So for B, when we're looking at orange, orange is lower frequency than blue. So I'm going to put O for orange over here, and look what we end up with. We end up with absolutely no photocurrent. Doesn't matter if it's super bright because there's nothing. Absolutely nothing. So no current. Cool. And again, the point of this is just if we're above the threshold frequency, we're going to have photocurrent. And if it's bright, we'll have a lot of photocurrent. If it's dim, we won't. If it's below our threshold frequency, we have nothing. No photocurrent whatsoever. Cool. I think that's just some space to work that I forgot to get rid of. So, here's a scientist I'm sure you may have heard of once or twice, Albert Einstein. Einstein did a lot of really interesting thinking. Just crazy stuff, actually, Einstein. Brilliant thinker. He figured out the photoelectric effect. And we had our first real evidence of wave-particle duality of EMR. So this is the first evidence that EMR is behaving not only like a wave, but like a particle, which is huge, absolutely huge. Lots of people know Einstein for E is equal to mc squared, which is fine. I mean, it's a super popular formula, I guess, if formulas can be popular. It's not actually what Einstein won the Nobel Prize for. Well, he won the Nobel Prize for this, figuring out the photoelectric effect. So let's go through and let's see what Einstein says about this. So first observation that he explained was this graph. Only with high frequencies do you get photocurrent. So essentially what he looked at with this, let me get a little bit nicer of a felt pen out. Skinny blue ought to work. Essentially what he looked at is he focused on the surface electrons, and we'll talk about why it has to be surface electrons in a second. And he said, okay, well, if those electrons, they're in there and they're attracted to all of the positives, it's going to take some energy to rip that electron out, right? Because it's happy where it is. So where is that energy coming from? Well, that energy is coming from a single individual photon. Not so bad, right? Not so bad. Now that one single individual photon, that particle or packet of light, has to have enough energy. If it doesn't have enough energy, it's not going to rip that electron out. That electron may absorb some of that energy. It may move faster, but then you know what? That electron's going to go somewhere else in the metal. It's not going to be pulled out, right? But if that one single photon has enough energy, and remember from last class, energy of a photon is equal to Planck's constant times the frequency. So we're talking actual frequency. If it has enough energy, it can rip it out. It can pull that electron away from its metal, away from its positives, and it becomes photocurrent, or a photoelectron. Cool. So let's go through this in a tiny bit more detail. Let's slow down and go through in a bit more detail. So let's first look at low frequency EMR. So I've got frequency that is below the threshold frequency. So one term that we want to look at here, so this is obviously measured in energy. It's W, so you probably think work. W is our work function, and it is the minimum energy needed to pull an electron out. Out. Call it, we'll say it like that. That works. So W is our work function, and it's the minimum energy needed to pull that out. So my work function might be 10 electron volts. That's how much energy it takes to rip that electron out. If my incident photon, for some reason, has less than that, so I don't remember if I put a number with that one or not. If my, let's just call it 8 electron volts. So the photon has energy that corresponds to 8 electron volts, and a frequency that corresponds to 8 electron volts. There's no way that it can pull that electron out. It takes 10, it only has 8. You're not going to pull it out no matter how hard you try. Kind of makes sense? Cool. So let's see. I think what happened here? Skipping around a little bit. Okay, let's say that now had the minimum frequency to pull it out. So our actual frequency that we see is the same as our threshold frequency. All of a sudden, so this would be 10 electron volts. That's my photon energy. And the work function, the amount of energy, is 10 electron volts. Could it pull that electron out? Absolutely. Absolutely. I should mention with this, I'm kind of skipping around a little bit here. Apologies for that. If the work function is the minimum energy to pull it out, can you see why we're talking about surface electrons? So work function is a minimum amount of energy required to rip an electron out. Work function is for surface electrons only. Well, if it's a deeper electron, it's going to take more energy to pull it out. And the only thing that's really consistent for those deeper electrons, or for the whole thing, is the surface electrons. So this one right here might take the most energy. This one might take somewhere in the middle. Only surface electrons, only ones that are right on the surface, will be consistent that we're going to look at. Okay, anyways, it's minimum for that reason. So now we can actually pull this out. What I'm also going to show you right now is we've actually got a formula for work function. Oops. So our formula for work function, again, the minimum energy needed to pull an electron out is equal to H times F naught, right? Because the minimum energy corresponds to the minimum frequency. No problem, that makes sense. We could expand this even a little bit more. We could say it's HC over lambda, but it's not just any lambda. So this is not in any physics textbook or anything. This is just something I do to make it simple. Call it lambda naught, right? So we know it's not the actual frequency of the photon. I mean, in this case it is, but it's typically not the actual frequency or wavelength of the photon. It's just the minimum frequency or the maximum wavelength we would need to rip that out. Cool, so we've got formulas. I believe this one is on your data sheet, but this one, not so much. Cool, okay, let's check this out. Let's see this in action. So it tells us the minimum energy to emit an electron from a metal is 3.55 electron volts. Cool, so if that's the minimum energy, we should recognize right off the bat that that is our work function. Determine the maximum wavelength of EMR required, and we want to answer in nanometers. So absolutely we can do this. If you want, you can even put the video on pause and try it on your own. Like this one is right up our, right up our alley. So we're going to start with that new formula that we got for work function. Work function, the minimum energy, is equal to Planck's constant times the threshold frequency, but we could take that one step further. And again, no textbook or anything is going to say this, but we could use HC over kind of like our threshold wavelength. And because we're looking for the maximum wavelength, we can kind of get rid of this one and just say, oh, well, work function is equal to HC over lambda naught. Now, if you forget about this, right, that this formula works as well, you can always solve for your threshold frequency and then use our universal wave equation to solve for the corresponding wavelength, right? We're good though. We can go ahead and do this. So wavelength, that's our maximum wavelength, is going to be equal to hc over the work function. So perfect. We start to plug in numbers. Planck's constant, we've actually got two values for that, so we got to figure out which value we are going to use. So let's see. Work function is given in electron volts, so I think I'm going to use the Planck's constant in electron volts. So let's see, 4.14 times 10 to the negative 15 electron volt seconds times the speed of light, 3 times 10 to the power of 8 meters per second, divided by our work function, which was 3.55 electron volts. Take a moment to plug that into your calculator. I think we end up with 3.49 times 10 to the negative 7 meters. The question specifically asked us for nanometers. So if we divide that by 10 to the power of negative 9, that works out to be 349 nanometers. So if we do the conversion. Perfect. And again, that is our minimum wavelength. Now, like I was saying before, we can kind of expand on this formula to use our two different sides of it. We could have solved with, maybe I'll use a different color here, just to be super clear. We could have solved with, very slowly get a different color. Work function is equal to hf naught, because that's what's actually on our data sheet. So once we solve for f naught, we can go through and we can say, let's see, c is equal to frequency times wavelength. That's our universal wave equation. And we'll just solve for the corresponding wavelength. Same thing, just 2 steps as opposed to 1. Cool, so we've talked about the work function. It's a bit of space for me to work. Next one to talk about is, what are these high frequency EMR pieces? So I'm just going to make something up here. I'm going to say 15 electron volts is my photon energy. So whatever frequency corresponds to 15 electron volts. Well, I've got that electron. It only takes 10 to pull it out. That means I'm going to have 5 electron volts left over. Any ideas what's going to happen to this? If you're thinking it's going to go into the kinetic energy, then you are absolutely right. If you weren't thinking about that, now you know. So it's going to go into the kinetic energy of that electron. And what we're looking at here, I used 18. I thought 15 for some reason. So anything that's left over goes into the kinetic energy. And one thing I guess that I should mention here, it is our maximum kinetic energy that we're talking about here. So the minimum energy to pull it out corresponds to our maximum kinetic energy. What if it was a deeper electron? Right? It's going to take more energy to pull it out, which means we're going to have less kinetic energy left over afterwards. In other words, it's going to be going slower. And I can actually show you with this little thing that we've got over here. So this is again off of the PhET website. So I've got a photoelectric device. It shows me the current in the bottom, the battery we'll talk about later when we talk about Milligan again. And I've got my intensity. So as long as my wavelength and my frequency, while my wavelength is smaller than my maximum wavelength, or my frequency is larger than my maximum frequency, we should have, that's still a felt pen, we should have photocurrent. So let's turn that up a little bit. Nice. All right, there we go. We've got some photocurrent. Look at that. And you'll notice that you've got some of those electrons going really, really, really fast, right? And it's almost like they're all going like a maximum speed. And then other ones we've got going significantly slower. So the ones that are going the fastest that you see right now, those are our surface electrons. And any that are going slower, those must be deeper electrons, so it took more energy to rip them out. Again, the only constants that we really have with this is the minimum energy, and therefore the maximum kinetic energy, which is our surface electrons. Cool. So I'm going to go back a little bit here, because we're actually going to build a formula. This is, any guesses actually before I start writing it? Any guesses what the, also I need to get a better felt pen. Any guesses what physics principle we're talking about here? It's all about energies, right? So if you're guessing physics principle 5, Nice work. Physics principle 5 is always ETI equals ETF. So in this whole thing, what type of energy are we starting with? We're starting with photon energy, so from the actual photon. Nice. And then where does that energy go? Well, part of the energy goes into the work function, just the energy it takes to rip that electron out. And if there's anything left over, it goes into our kinetic energy. And again, the only way that we can have this constant is by dealing with the minimum energy, those surface electrons. So there we go. This is our formula. This is what we'll be focusing on for the next little while. This lesson, and you know what? Honestly, next lesson too. Okay, second example that we've got here. Second example. We've got the work function for a metal is 7.2 electron volts. Then we've got, I can't read right now, 4.0 times 10 to the power of 15 hertz EMR that's shone on the metal surface. Determine the maximum speed of those photoelectrons. So first off, let's get things a little bit straight here. So the work function, that's fairly straightforward. That's W. If we really wanted to look at it, we'd say that's H times F naught, which is just our minimum frequency. We don't really need this part, but I'm going to leave it up there because this 4.0 times 10 to the power 15, that is not my minimum frequency. It's saying that that light with 4.0 times 10 to the 15 hertz frequency, that light is actually being shone. So this is my actual frequency, my real frequency that's being shone on it. Okay, it says determine the maximum speed, so V is a question mark, of the photoelectrons. Really doesn't look like it's giving us that much information. But let's go through. Let's start with physics principle 5, ETI equals ETF. So we're starting with that photon energy. That photon energy is going to, 1, rip the electron out. That's my work function. Plus anything that's left over goes into my maximum kinetic energy. Cool. So I guess the question is, if we could find our maximum kinetic energy, and I know a formula for my maximum kinetic energy is 0.5 mv squared, I could go ahead and solve for the speed, right? And we could do this in one great big step, or we could do this in a couple smaller steps, but just kind of thinking ahead here. And you know what, we'll expand and then we might have to come back to something. So the energy of the photon, we're given frequency, so I'm just going to use photon energy with frequency, h times f. And again, that's my actual frequency, is equal to the work function. Well, that's just the work function. We don't need to do anything with that because it gives us the actual value, plus my kinetic energy, which is 0.5 mv squared. Cool, now here's the question. You don't need to write this out. It'll get messy if you do. I'm going to erase in a second. When I use this formula for kinetic energy, 0.5 mv squared, what are the units? Joules. When I use work function, what do you think the unit should be in? If you say electron volts, you can't add electron volts to joules and get anything that makes any sense. So it has to be in joules. And if those two are in joules, any guesses what Planck's constant needs to be in? Joules. Okay, so let's go through, and we might need to do a conversion before we start off with anything here. So let's do that. 7.2 electron volts. Let's change that into joules. So work function is, am I going to have space to do that over here? I might not have planned out my space very well. 7.2 electron volts. I want to multiply that by, let's see, I want to cancel out electron volts. I want to end up with joules. So it's 1.6 times 10 to the negative 19 joules for every 1 electron volt. Excellent. And then my work function, let's plug that into our calculators. I think 1.152 times 10 to the negative, let's see here, negative 18 joules. Now we've got everything in joules. Now, again, we could either solve for the kinetic energy first, rearrange, solve for that one, and then plug it in, solve for the speed, or we could do it in one big step. I might do it in one big step because I'm kind of already set up for that. So let's see. I'm going to subtract work function from both sides. So it's going to be hf minus the work function is equal to 0.5 mv squared. Let's see, then I want to divide both sides by 0.5 and m, so we can cancel those ones. Then I gotta get rid of the squared, so I'm gonna take the square root of both sides so I can get rid of that. I've got a huge mess on my hands now, so I'm just gonna rewrite my maximum speed is gonna be equal to the square root of hf minus w over 0.5 m. Nice. I think we've got everything we need. We can plug in numbers. Again, if you wanted to do this in a couple smaller steps, that's no problem. Like you could solve for the photon energy, you could solve for uh, well, you could solve for an entire half of the equation realistically, solve for kinetic energy, and then you could solve for speed. We'll do it all in one big step here. So I need my work function to be in joules, so I just want to double check before I screwed up. 6.63 times 10 to the negative 34 joule seconds times the frequency, 4 times 10 to the power of, I think it was 15, but I better double check, 15 hertz. We're going to subtract from that our work function, which we just figured 1.152 times 10 to the negative 18 joules. Cool, and then we're going to divide this by 0.5 and by a mass. And we haven't talked about a mass yet, right? But what are we looking for? We're looking for the speed of an electron, and we're talking about the kinetic energy of an electron. It's a photoelectron, but it's still an electron. So what mass do we think we're using? If you're saying mass of electron, yeah, nice. So 9.11 times 10 to the negative 31 kilograms. And then don't forget, this whole big thing goes under the square root. So take a moment, you can put it on pause if you want to, and see what we get for the speed of this photoelectron. So if you ended up with 1.81 times 10 to the power of 6 meters per second, that is just awesome. Most excellent. That's what I end up with too. And that makes sense, right? When we were talking about Unit 2 stuff like 10 to the power 6, that's totally reasonable for a single individual electron. Nice. So the very, very last thing, and it seems like a while ago that we talked about this one, but how does Einstein's explanation tell us about photocurrent versus intensity? Right? So bright light, assuming that it's above the threshold frequency, bright light makes high photocurrent, dim light makes low photocurrent. This is actually super easy. So we're talking about individual photons. One photon can kick out one electron. What do you think 2 photons could do? Kick out 2 electrons. What about 3 photons? 3 electrons. There is our direct relationship, right? Each single photon can kick out 1 single electron. That is like the definition of a direct relationship. So perfect. Just a quick summary of this, because we covered a lot of stuff today. You need to know those 2 graphs, right? So photocurrent versus frequency and photocurrent versus intensity. So know those 2 graphs and understand those 2 graphs. And then understand how Einstein's equation plus EK max corresponds to those 2 graphs and how we can use that equation to go through. Work function dealing with the minimum amount of energy, which is our minimum frequency, corresponds to our minimum frequency or our maximum wavelength. The energy of the photon, you know what, I'll expand this even a little bit more. So energy of the photon is equal to HF or HC over lambda, right? And that's my actual frequency or my actual wavelength. My work function is H times F naught. That's just my minimum frequency. It doesn't necessarily have anything to do with my actual frequency. And then we could also write this as HC over lambda naught, but you don't really see that one as an actual formula. Right, so that's just something we have to recognize. And then for now, what we've got is EK max is 0.5 mv squared. We're going to learn a new one for that in the next lesson. And you can realistically use any combination of these to find what you're looking for. Cool. So that is it. This is a pretty cool lesson. This is pretty neat stuff that we've got here. I really enjoy it. I hope you are too. Make sure you're doing a bit of the practice, doing the things that you need to know how to do, and we will talk to you again soon, Physics 30s. Bye for now.